All right, thank you, Ida, and welcome everybody. So today I'm going to be giving you an introduction to tclean, and just to start off with, I want to go over the software that we'll be using in this tutorial if you're following along. So everything has been tested in CASA 6.2, and you can obtain this version of CASA at casa.nrao.edu under previous releases. And if you want to use CASA and just learn more about it, there's really good documentation online at the CASA docs. There's a recently accepted paper that was written by the CASA team if you'd like to learn more about the software. And I'll also be using the analysis utils Python package, which can be also downloaded. And there's a CASA guide on it as well if you want to learn a bit more about that. So let's get started. So the data that I use in this tutorial is data that's from, is used in a number of the ALMA guides. This is from an early ALMA project searching for H2D plus in the disk of TW Hydra. And we'll specifically be working with the N2H plus J equals 4 to 3 line. There has been a paper published on this data by Key et al. In 2013, if you'd like to read a bit more about the science that was done on this. Okay, so right here, we're going to start off with getting familiar with tclean. So if you have CASA open, you can type in tclean, and you'll see a long list of parameters come up in CASA in front of you. And so tclean has a lot of parameters that allow you to really adjust the cleaning process to whatever you desire. And tclean's main goal is to do image reconstruction of radio interferometric data. So we'll be going through these main parameters that I have listed on the slide here in detail throughout this tutorial. But before we get to those subparameters, I would like to also just give a brief introduction to synthesis imaging. So synthesis imaging is essentially what tclean is implementing, and it's demonstrated in this figure here that's within the CASA docs, and you can go to the CASA docs to kind of read a bit more detail about this process. But it is essentially an iterative process to try and remove the dirty beam from the source brightness distribution. And very briefly, I'll go through the cycles that tclean does in the imaging process. So there are major and minor cycles. In the major cycle, you have your data, your visibilities, and if you've already done some cleaning, you'll have a model of your source as well. And this model ends up being subtracted from your data to produce what is called the residual image. This image is then gridded to a uniform UV plane, and then inverse Fourier transformed into the image plane to enter into the minor cycle. And we'll talk a little bit more about the minor cycle later in the talk. But just to introduce it here, the minor cycle will essentially use whatever specific clean algorithm you've specified to generate a model of your source, and then to sort of do this iteratively and subtract it from the residual image that you've input from the major cycle. This model image is Fourier transformed back into the visibility plane, brought back into the major cycle, and is degridded, and then that is subtracted from your data. And this just keeps going on iteratively throughout the clean process until it hits a major stopping threshold. So that was my very short summary of a very complicated process, but we'll go through the parameters now in this talk, and hopefully these individual steps will make a bit more sense too, as I'm talking about the individual subparameters. Now, because this talk is focused primarily on tclean, there are some imaging preparation steps that I'm not going over in this tutorial, but I did want to mention them. So I have just a couple of them listed here. The first thing you should do in most imaging cases is inspect your data. And I highly recommend looking at the weblog. So you should have a weblog with any data any ALMA data that you have. And there's actually an iTrain on how to do ALMA weblog inspection. So I suggest checking that out. We'll also talk a little bit about listobs and plotms, which are two CASA tasks that are very useful in inspecting your data. So listobs can be used to just get general information on what is in the measurement set, that is the data the ALMA data that you'll be imaging. And plotms can essentially be used to visualize the data in your measurement set. So you can do things like check for the UV coverage of your data. You can check to see if there's spectral lines in your data or telluric lines, which are also things that won't come up in the image, but are visible in the UV plane. So looking at your data in plotms for these lines is the primary way that you can see if they're there in your data. You'll also usually want to do a couple steps to prepare a measurement set for imaging. In some cases, a measurement set might have calibrator data still in it. And so it would be a good idea to split just the science source out into its own individual measurement set. This will reduce the size of the measurement set and will make some CASA tasks actually run faster. If you're doing continuum imaging, you might optionally want to split out a continuum only measurement set, and similarly you might want to make line only measurement sets, but it really depends on what you want to do with your data. And if you're line imaging, there are cases where you might have to do UV continuum subtraction, and in particular if the continuum is stronger than about 3 sigma per channel, then you should do UV continuum subtraction before you go on to imaging. I've listed here a couple of additional resources that go into imaging and are just general tutorials. So there are a number of CASA guides that you can find online, and there's also this video tutorial that I've linked here. So the first parameter that we'll talk about is the select data parameter and all of its subparameters. So this is probably the easiest step of cleaning. So just deciding which data you want to image, and you probably already have a good idea of that. If you're following this tutorial along, you already have the TW Hydra measurement set, and that is what I have put into the viz variable here. So we're working with the continuum subtracted data. I've also specified the field and the spectral window here, but there's also a number of other parameters that you can specify if you would like to limit the data that you're actually imaging. So time range, UV range, antenna scan, observation intent are all options for adjusting the data that you're going to image. Now, if you don't know what's inside your measurement set, if you don't know what the spectral window IDs or field IDs are, the first way that I would suggest getting this information is either to go to the weblog, which will give you also additional imaging parameters that can be useful for you to look at, and it's a lot faster than looking these things up in the ways that I'm describing now. But in the case that you can't get that information, or you'd like to take this approach, you can actually use listobs to get that information. So you can run listobs two ways. You can run it and just have it output to the logger, or you can specify a list file and it will save the output to a text file. So listobs will essentially give you information on the observations that were done, when they were done. It will give you field information, which will include field IDs, and spectral window information, which will include spectral window IDs. You can also find antenna information in there as well. So it'll look a bit like this. So this is just the very first chunk of the listobs output that I'm showing you here. But we're primarily interested in, for our case, what the field IDs and names are and what the spectral window IDs are, because that's what we want to put into tclean for imaging. So we have a pretty simple case here, because in our measurement set, we just have TW Hydra, and we have one spectral window. So I've already put this in. But just to show you again, this is our data selection for this tutorial. Now, the next step is to set some imaging parameters. And I'm just listing a few of them here, and I'll go into a bit more detail about them in a few moments. But essentially, these are the size of the image that you're creating in pixels, and you need to also give a cell size. So cell size is the pixel size in your image. Phase center is also highlighted in blue here because that's, particularly important in the case where you are doing a mosaic and you need to pick a phase center, and this typically needs to just be a pointing near the center of the mosaic itself. Because we have a single pointing in our data, this is a fairly easy choice for us. I also want to mention that the data column here, it usually defaults to the calibrated data column. And because we have split out both our source and the calibrated data into its own measurement set, that calibrated data has actually been moved into the data column. And sorry, I should have said corrected column. It's data or corrected column. And then you should also give an image name here that kind of makes sense. And I've just selected TW Hydra N2HP 4-3 because that's what we're imaging. Now, if you haven't been able to find cell size or you want to figure it out yourself, there's a couple of ways. So I just thought I would show you quickly how you can do this using two different methods. So the first method that I would suggest is using plot-ms. So you can actually plot the amplitudes of your data as a function of UV wavelength to do this. And so I'm showing an example of this plot-ms command here. And whenever you're using plot-ms, especially on a larger data set, you should try to do some type of data averaging. So I've demonstrated doing time averaging here and averaging with scans, averaging across scans. In the case where we're trying to figure out what a cell size is, you should avoid baseline averaging. So to determine the cell size, you essentially plot amplitude versus UV wavelength, and then you find your longest baseline in UV wavelengths, and you can plug it into this equation that I have here on the screen. And then we typically recommend doing 5 to 8 pixels across a beam. So make a choice of how many pixels you'd like to have roughly across your beam, plug that into the equation, and then you can get an estimate of what your cell size should roughly be. And in this case, I've picked 5 pixels, and this gives me a rough estimate of about 0.1 arc seconds. You can also use the analysis utils package. But the thing to keep in mind is that this doesn't account for the projection of baselines. So we can actually see that the cell size it gives is slightly larger than what we've already estimated using plot-ms, so about 0.12. But you do have the option of sort of iterating the imaging process if you would like to adjust these parameters. To determine the image size, there's also a couple of ways that you can do this. If this, again, this should be in the weblog, but you can also take a look at what essentially, if you have a mosaic, you can use the analysis utils plot mosaic command, or you can use the command we've already seen on the previous slide, pick cell size, and it will give you an estimate of what your image size should be in pixels. In general, your image that you're doing should be larger than the primary beam extent, especially for non-point sources. You should select symmetrical values and typically round up to the nearest 10 or 100 pixels. And CASA will usually tell you if you're not picking an efficient source size. And this, I've just thrown up the equation here for the primary beam. If you know what the wavelength you're observing at is, and if you know if you're using the 12 meter or 7 meter array, you can use this equation here to determine the primary beam of a single pointing. So if you have a mosaic, it is good to just sort of visualize the extent because it becomes a bit more complicated. In our case, we just have a single pointing, and we can kind of see here that its extent is roughly 20 arc seconds across each side. And so the pixel size that I actually end up choosing is about 240 pixels for a cell size of 0.1 arc seconds. And my phase center is the 0 field. So another thing that you'll need to select is the spectral mode. And in most cases, you're either going to select spec mode equals MFS, which stands for multi-frequency synthesis, or you'll select spec mode equals cube. There are a couple other options. And if you want to know more about those other options, you can definitely check them out in the CASA docs. In these cases, if you choose spec mode is equal to MFS, this is essentially telling tclean to synthesize all of the channels in your cube into a single image, which is continuum imaging, and this is demonstrated on the figure on the left-hand side. If you choose spec mode equals to cube, this is telling tclean that you want to image all of those channels separately into a data cube. And when you select spec mode cube, you actually end up with a number of subparameters that you should also adjust. So I'm going through these here. You'll need to give channel information into tclean so it knows just where in the cube you want to start imaging, how many channels you want to image, and how wide you want your channel width to be. And these values can be specified in terms of channel number, frequency, or velocity. And for simplicity, I'm just specifying them in terms of channel number here. And so nchan equals 30. So I'm telling tclean I want to image 30 channels. I want to start at the 230th channel. And I want my width to simply be one channel. So a single channel that corresponds to the original width of the channel. We could bin if we wanted to, and we could pick a width equals 2, but we would need to reduce the number of channels to compensate for that. And because we're looking at a Milky Way object, our redshift is 0. So we don't need to worry too much about redshifting of the lines, and I'm just inputting the rest frequency of the N2H plus line here. If you have low redshift sources, this is usually sufficient. You can look up the rest frequency of lines with Splatolog. It's also going to be probably in the header of your data. But yeah, it really depends on what you would like to see with your data, what you put in for the rest frequency here. And finally, I'm setting velocity parameters. So I've set our out frame to LSRK. So this sets the LSR's kinematical radio definition, and I've selected vel type equals radio. So radio is recommended, but there are a number of options. So please see the CASA docs if you would like to see what these other options are for both vel type and out frame and their precise definitions. And one thing to keep in mind is if you use radio as your velocity type, this produces channels of fixed velocity width, which is sometimes useful. So this is just a summary of the inputs. So radio was default, so it doesn't get, so the color doesn't change when we do inp tclean again. But if you're following along, this is what you should have put into tclean. So I wanted to briefly mention the gritter. So this is actually not a trivial process, but luckily tclean does this for us. So the gritter is responsible for resampling the imaging weights and weighted visibilities onto a uniform UV grid. In the case where you have a single pointing, you will just need to use the standard gritter. And this essentially applies operations in the image domain to correct for direction-dependent effects. If you have multiple pointings and you have a mosaic, you would want to use the mosaic gritter. And this also applies, in addition to direction-dependent effects, time variable and baseline-dependent corrections in the visibility domain. And there are a number of other options again, so please check out what there is in the CASA docs. So for this tutorial, we will just be working with the standard gritter. Okay, so I want to talk a bit more about the minor cycle clean algorithms. And before I do this, before I talk about the specific deconvolvers, so these clean algorithms, I wanted to introduce what deconvolution is in general. And so our data, as we get it from the telescope, is represented by the image that is shown here on the left in this figure. So we start out with a dirty map. And that's of course, if you've imaged your data. So this dirty map is essentially your source brightness distribution convolved with the telescope PSF, or the dirty beam, which is in the middle of this figure here. And ideally, we want to essentially remove this telescope PSF from the source brightness distribution to be able to do science on our data. And so the deconvolution that's performed attempts to separate these two things. And the way that these algorithms do this is by modeling your source. And so the modeling is done in tclean in the minor cycle, and depending on which deconvolver you've selected, it will either assume that your source is a collection of point sources or some kind of extended paraboloid. Now, there are a number of deconvolvers that are available to you in tclean. But they're all useful for very specific cases. So I'm going to go through the recommended ones here. So the first one is the Higgbomb clean. So this is an adapted version of the original clean algorithm. And this essentially assumes that your source is a collection of isolated point sources. This is compute intensive because it performs the minor cycle iteration using the entire PSF. So it essentially subtracts the entire PSF from your image. The Clark deconvolver is actually a bit faster because it does essentially what Higgbomb does, but only takes a smaller patch of the PSF. So if you know that you have a very isolated point source, then Clark might be a better option for you. In many cases, though, your source is likely not a point source, and so it's actually better to use multi-scale clean. And multi-scale clean is designed to be scale sensitive, and you can actually specify multiple scales. And so in this case, the actual model that is assumed is an extended tapered paraboloid, sorry. And there are two subparameters to the multi-scale deconvolver, and that is the scale subparameter, where you can list a number of scales in pixels. And so just to keep in mind, you should only use relevant scales here. So set the scales up to like the smallest axis of like asymmetric emission, essentially. And it's also recommended to always include a point source scale, which corresponds to pixel scale 0. You can adjust how much weight tclean gives to the scales that you've included in that list. So there's a parameter called small scale bias, and it can be varied from -1, which will bias towards larger scales, to 1, which will bias towards smaller scales. And the default value is 0. And we're just working with the default value here. So I have picked the multi-scale deconvolver for this imaging example, this tclean example, and I've specified 3 scales here. So I have 0, 5, and 10. So this is specifying a point scale, a scale that's roughly our beam size, and then a scale that's roughly 2 times our beam size. Now, weighting schemes are also really important in tclean and in imaging interferometric data, and that's because visibility weights actually alter your synthesized beam and the dynamic range of the output image. And this is, a very powerful thing to do. One thing you can do is smooth an image in the image plane with, a Gaussian or some other shape, and you can lower the image of your data, lower the resolution of your data this way, but it doesn't actually change the dynamic range of the output image the way that the weighting scheme does. So this is actually a stronger way to change, the resolution of your data, or adjust the resolution of your data. So I'm listing off sort of the main weighting schemes that tclean offers here. And the first weighting scheme that I'm going to talk about is natural. So in natural weighting, the visibilities are weighted by the data weight. So essentially by how noisy the data is. And so what you end up with natural weighting is a slightly lower resolution, so a larger beam, and but a lower RMS noise because you have a larger beam. And the reason you end up with a larger beam is because typically these longer baseline data points, which are on the outer edge of this sort of UV distribution here, those typically have a higher RMS noise, so they're down-weighted when you're using the natural weighting scheme. Now, uniform weighting is the next option here, and this instead weights visibilities that are in the same UV cell uniformly. So this has the effect of actually reducing side lobes, but it also gives you higher resolution than natural weighting, but as well as a higher RMS noise. Now, what's used most commonly and is sort of the default in the imaging pipeline is to use Briggs weighting. And this is a compromise between natural and uniform weighting. There is a subparameter, the robust subparameter, that you can use to sort of adjust just how much weight you give to natural-like behavior or uniform-like behavior. So if you set robust to -2, this mimics uniform-like weighting. And if you set it to a +2, it mimics natural-like weighting. Very often, the imaging pipeline will put out robust parameters of about 0.5. I also want to mention UV tapering here because it is really another powerful thing that you can do with your data. So if you want to either increase the sensitivity of your data and you don't mind degrading the resolution of your data, you can use UV taper. And this essentially applies a Gaussian taper to your UV data in addition to the weighting scheme that you specify. And so in most cases where you're using UV taper, you'll likely want to specify, if you're using Briggs weighting, a robust parameter of 2 to get natural-like weighting or to use natural weighting. Now, keep in mind, tclean has only implemented an outer taper so far. But if you do want to sort of limit the inner range of your UV data, you can apply, essentially, you can clip the UV data using the UV range parameter in our data selection that we saw very early on in the talk. This is a figure from the CASA docs that actually shows us what these different weighting schemes essentially produce with our PSF and how it changes the image of our data. So you can see that natural weighting has a slightly larger beam size and larger side lobes here. We have, and then we can take a look at our observed image underneath that. I want to jump to uniform because that makes more logical sense to me. So uniform weighting produces, as we can see, a smaller beam size as well as smaller side lobes. And you can see the image looks nice below that, whereas robust gives us a nice compromise between the two. So you can definitely see when you're looking at robust, it is definitely a compromise between natural and uniform weighting. And then we have a tapered example here where we just have, we've clearly degraded the resolution using the taper here, but we have also increased our sensitivity and we've also reduced side lobes. So for our example, for the TW Hydra data set, I am working with the Briggs weighting initially, and I'll give an example of tapering at the end. And I'm selecting a robust parameter of 0.5. And so this summary of the last three parameters we've talked about, just looking at imp tclean output again, we're using standard gritter, multi-scale deconvolver as well. Now, masking is an important part of the imaging process because masks essentially tell tclean where the minor cycle algorithm should look to put clean components. So this is really restricting the region where our model gets put down for our source. So this is really useful. And there are a couple of ways that you can actually define a mask using tclean. So some people prefer to create masks by hand, and there are many cases where this is useful. So I'll show essentially what the GUI looks like a little bit later on in the talk, but you can create your own mask either interactively while you're cleaning the data, or you can input a mask image file, a region file, or a region string. So if you know your source really well, for example, TW Hydra is a disk. So you could, for example, put in a Keplerian mask if you wanted to. You could put that in as an image file and it would, make imaging fairly straightforward for you. Now, auto multi-thresh is another option for masking that I'd like to mention because it can be really powerful and helpful in the case where you have a lot of spectral line emission or extended sources in many channels. And yeah, so as I put here on the slide, it makes spectral line emission masking much easier and faster. So auto multi-thresh is available in CASA versions 5.1 and later. And there is a paper that was published in 2020 on this algorithm by Kepley et al. If you'd like to check that out. And there's also an auto masking guide, which I'll be referring to, that's very helpful for getting familiar with auto masking. So we'll be using the auto multi-thresh masking procedure in our example. And so I've put up a list of subparameters that we'll be adjusting in this tutorial. But I do want to highlight that there are more than I've just shown here on this slide. So check out the information on these subparameters if you're interested in learning more, because it really does allow you to tune how the auto masking performs. So I wanted to go through the general process that auto masking does. And these are the three general steps. So in the first step, auto masking will set an initial source mask. And the input parameters that are relevant for this in tclean are the noise threshold and side lobe threshold. And you essentially put in signal to noise ratios for these parameters, which is really powerful because you don't have to actually measure an absolute noise or know what the noise is before you start imaging. You just need to say, I would like, to set noise threshold of, 2, a signal to noise of 2 or something like that. And similar for side lobe threshold. So auto masking will calculate these two threshold values, will calculate the absolute values of these two thresholds, and then it will select the higher of the two. And so in this image here from at the top from Kepley et al., it's sort of showing you what happened in this for this particular case. So we can see that from this image, the noise threshold value is actually lower than the side lobe threshold value. So auto masking picks the side lobe threshold value to create the initial mask. Now, the second step that auto masking takes is the pruning step. And so the relevant input parameters for pruning is, I have listed here, min, beam, frac. So essentially, you can specify a minimum beam fraction of the clean or the mask regions that you want to keep within your mask. And this allows you to remove any spurious masks that might be, just picking up sort of large regions of noise. And this is demonstrated in the central figure here, where we have the residual image, the mask before pruning is applied, and then the mask after the pruning is applied. So once we have done these first two steps, we then have the option of expanding our mask to include lower signal to noise regions that might not have been picked up by the masking process. So this could be really valuable, again, for like extended sources. So the parameter I've listed here is low noise threshold. It's not the only parameter that adjusts how these masks are expanded, but it is the one I just wanted to highlight. So essentially you pick this low noise threshold, tclean and automasking will essentially expand that mask down to the low noise threshold that you specify. And this is shown kind of in the lower bottom figure here, where the threshold only mask ends up being smoothed and expanded out to this threshold we specify. So the behavior of automasking is also going to depend on the UV coverage of your data. So in the automasking guide, there's actually a table that you can use to determine which values you should input for the parameters that we've talked about so far. This is meant to be used as a guide. You might need to adjust it depending on what your case is. But if you're using this guide, essentially what you can do is check what the 75th percentile is of your baseline stats. And you can do this using analysis utils. And when you get that number out, you can determine whether it corresponds to a 12-meter short scenario or 12-meter long baseline scenario, or if you have 7-meter, that's sort of its own unique scenario. For our data, the baseline, the 75th percentile of our baselines is 197.4 meters. And so this corresponds to the 12-meter short scenario. So we take these values, and that mainly means that we need to change side lobe threshold to a slightly lower value of 2 and the noise threshold to a slightly lower value of 4.25. So these are the inputs for our case for the TW hydro data. And before we can clean, we actually need to set the stopping thresholds. So I have set n iter, which is the maximum number of iterations that clean can run, to a very large number. This essentially ensures that what determines the stopping threshold is either determined by sort of the automasking that I've selected, but I've also specified here this parameter n sigma equals 2. And this is telling clean that I would like to do an RMS-based threshold stopping at a signal to noise of 2. And this is something that you could also do by setting the threshold, which would be an absolute value of RMS noise. But if you're using automasking or auto multi-thresh, it'll essentially also use the thresholds that you specify in auto multi-thresh at the earlier step 2. And it will decide per channel where that threshold should stop. I've also selected interactive equals true here. And in general, I recommend doing this, especially if it's a first iteration of imaging and you're either doing manual masking or you're using auto multi-thresh, just to be able to check that the masks that are produced make sense. So this is just a summary of all of the tclean inputs that we've gone through and that are changed from the default for tclean. And I don't expect you to be able to put them all in, but if you're following along, you should have already put them in. Okay, so now we get to actually running tclean. So if you've been using the imp tclean command command, you can actually just type go in CASA and it will start running tclean for you. And it will eventually bring up this GUI that looks like this, which I'm showing on the screen here. So within this GUI, you can do a number of things. So you can inspect each channel using these arrows on the right-hand side here. And you can also create or adjust the masks using the shapes that are up here. So you can select square, elliptical, or you can even do sort of, you can do other different mask sizes. And once you're happy with all of the masks and you've inspected all of the channels, you can then choose to tell tclean to continue cleaning. So there are a few different options for this. So there's the next action buttons here. If you want to continue cleaning using an interactive mode, then you want to use this green clockwise arrow. This essentially tells it to perform some more iterations of clean, and then it will return the GUI to you to essentially change or inspect the mask again. If you think that you trust the mask that you have put down or that Auto Multi-Thresh is creating, you can hit the blue arrow to finish cleaning non-interactively. And if you actually don't want clean to continue, you can hit the red button to terminate tclean. And so this is just a couple of snapshots of a couple clean iterations. I wanted to show you how the masking how the masks adjust as we continue through tcleaning, and how the residual image changes. So after one iteration of clean, the GUI pops back up and gives me the image on the left-hand side, so we can see in this particular channel, the mask has been expanded, and we still see a little bit of source emission here. So we can run clean again, and then when it pops back up, we can see the mask has been expanded a little bit more, and there's a little less source emission here, but we can see that it's been, it's done a decent job at subtracting some of the source emission. So we let this process finish. So if you're following along, you could hit the blue arrow and you can let clean finish. And you'll end up at the end, when it's done, a set of output files here that I have listed on this slide. So you will end up with your image file, which in this case will be a cube. You'll end up with a mask, and this will be the final mask that tclean produces. So if you're doing auto multi-thresh, this mask file will be the last mask that's produced. There is an option to, I think, save all of the intermediate masks as well. So I would encourage you to look a bit more into the details of auto multi-thresh to see how that works if you want to be able to save all intermediate masks. You'll also get a model file. So this will essentially be the model that your minor cycle algorithm has produced of your source, a primary beam file, a PSF, and a residual image, and a weight image. And you might get other files for different imaging setups, but these are just what we're getting in our specific example. Now, at this stage, it's a really good idea to inspect all of these images independently to make sure that they make sense. So I'm just showing a few examples here where on the left-hand side, I've just taken the channel with the brightest emission of our source and showing that. And then in the center, I have the model of the same channel. And on the right, I have the residual image of the same channel. So the takeaway from the model here is that you can see that indeed tclean did use the multiple scales in the cleaning process. So we have some point sources here, and we also have some of our larger scales represented in this model. And when we look at the residual image, we want to look and see if there is any remaining uncleaned emission from our source. Because there doesn't really appear to be much of a difference between where we know our source to be in this channel and the noise or the residuals around it. Clean sort of did a sufficient job at cleaning the emission of our source here. Now, very briefly, I wanted to mention tapering and give you a very specific example of it, just to show you how you can do it. For our data set, tapering is not going to actually change that much because even though we have a somewhat extended protoplanetary disks, we don't have any extended emission that tapering will pick up on. But there are cases where you can have more blobby sources with extended emission, where that extended emission is not detected with your initial beam size. And I've seen this for some cases, for example, of data of nearby galaxies. So it can be really powerful to actually taper your data. Then you increase your beam size, but you're also increasing your sensitivity, and you might pick up emission in these more in these weaker regions that are not detected at your original resolution. So to do tapering, you need to essentially set the UV taper parameter, and you also need to remember to change your cell size and your image size depending on what your goal resolution is. And just as sort of a rule of thumb, if you want to estimate what this taper should be, you can use the IA.beam for convolved size CASA tool. So you can take your original resolution, put that in as your source resolution, and then put in your goal resolution, and it will spit out a size that you can put into UV taper to roughly get that resolution in your final image. This is something you might need to adjust, but it is like a good way to sort of initially guess what that taper should be. And so in my example, I've decided to take our initial beam of roughly 0.4 by 0.6 arc seconds and to taper it out to 0.8 arc seconds. And I have estimated what that UV taper should be, and I've put that into tclean, and I've also made sure to set the robust parameter to 2. I've put in a new image name, and then I hit go and let everything work. If you're using auto multi-thresh for tapering, I would really highly recommend that you monitor the mask, because this is also having an effect on the UV coverage of your data. So this might also adjust the masking behavior of that algorithm. So check that as you're cleaning. But in this case, you can just let it go on the TW Hydro data set, and your central channel of your cube should end up looking something like this. So still similar to our original image, but a bit more smoothed out. Okay, so these are the primary things that I wanted to cover today in today's talk, and I'm happy to answer any questions now.